Good morning, my name is Marlini. I'm a PhD researcher in the Cavendish laboratory at the University of Cambridge, and today I will present our work in phase field modeling of fracture and fatigue in shape memory alloys. Regarding the contents of this presentation, I'm going to talk first about shape memory alloys and their mechanical and fracture behavior. Then I will present our phase field fracture formulation for shape memory alloys, showing some representative results. And finally, I will deal the extension of such formulation to fatigue and its application to model fatigue crack growth in shape memory alloys. So what are shape memory alloys? Shape memory alloys are materials that undergo phase transformation from austenite to martensite phase upon the application of a mechanical load, a change in temperature, or both. And as a consequence, they show a non-linear response with very large strains, up to 10%, that are reversible as the material can recover its original shape by unloading or through a change in temperature. And of course, both mechanical and fracture properties change with this phase transformation. As shown in the left figure, two phenomena are intrinsic to shape memory alloys and their phase transformation: superelasticity, SE, and shape memory effect, SME. Only superelastic alloys such as nickel titanium can achieve full strain recovery when the load is removed, showing a hysteresis loop in the stress versus strain response. And shape memory alloys experience the shape memory effect, show a large residual strain after unloading, and require a change of temperature to recover their original shape. So in shape memory alloys, where both superelasticity and shape memory effect can take place, their occurrence is governed by the temperature of the system, as shown in the figure at the right. This figure shows a typical shape memory alloy stress temperature curve, where MF and MS denote the martensite end and start temperatures, while AS and AF denote the austenite start and end temperatures. So from a fracture mechanics perspective, what is more interesting is that the high stresses that are present at the crack tip will trigger a stress-induced phase transformation. And as a consequence, there will be a small region at the crack tip where the material is in its martensitic phase. In the slide, you can see that for a calculation of a stationary crack, so no phase field. On the left, you can see the contours of the martensitic volume fraction, and on the right, you can see the stress distribution ahead of the crack tip in a log-log plot. Far away from the crack tip, the stresses are governed by the austenitic material properties. Then there is a transformation zone, and close to the crack tip, the material is fully martensitic. And the key thing is that this stress-induced transformation brings some toughening of the material. And we not only want to model stationary cracks like this one, but also propagating cracks due to static or cyclic loading, to capture these toughening effects and predict the structural integrity of these alloys. So let's start with the phase field paradigm that is becoming very popular in many areas. We all know that from a computational or mathematical perspective, tracking the evolution of interface boundaries is challenging. The idea behind phase field methods is to use an auxiliary field to follow interfaces implicitly, so to say, in the sense that we no longer have a sharp interface, but the auxiliary variable called phase field or phase field order parameter, which tells us where the interface lies. So for example, in the case of fracture applications, the phase field can take a value of 1 in the cracked phase and of 0 in the undamaged material points, varying smoothly in between. The temporal evolution of the phase field variable is then described by a differential equation that can be easily solved using standard numerical methods, making the tracking of evolving interfaces computational tractable. The method was first developed in the microstructural evolution community, where the change in shape and size of microstructural features, such as grains, can be predicted by defining the evolution of the phase field in terms of other fields, such as temperature, through a thermodynamic free energy. While in fracture mechanics, in the application that I will be mainly discussing, the phase field tracks the crack-solid interface, enabling the capture of complex cracking morphologies. You can see in the figure examples of crack merging, nucleation from arbitrary sites, branching. So it is a very powerful tool from a computational perspective. So at this point, you might say, okay, all good on the computational side, no issues dealing with evolving interfaces such as cracks. But when do those cracks propagate? Or in other words, what differential equation do you use to evolve the phase field? Well, one of the nice things about phase field models is that they provide a computational framework for Griffith's energy balance. Griffith, one of the fathers of fracture mechanics, postulated that a crack would grow if the energy released by the solid reached the critical value, the so-called critical energy release rate or material toughness, GC. This energy balance is the result of considering, in a thermodynamics context, the work required to create two new surfaces. One can formulate Griffith's energy balance in a variational form, with the term accounting for the stored elastic energy in the solid as given by the strain state, and the second term characterizing the fracture energy, the energy dissipated by the formation of a crack. Therefore, crack nucleation and growth can be predicted naturally without ad hoc criteria as dictated by the minimization of this energy conservation statement. However, minimization of the Griffiths functional is hindered by the fact that the crack surface gamma is unknown. And here is where the phase field paradigm comes to our rescue, because we can use the phase field as a marker, transforming the surface integral into a volume integral, enabling us to solve this global minimality problem. Two things that I want to emphasize here. First, following standard continuum damage mechanics arguments, the phase field can be thought of as a damage variable that goes from 0 in intact material to 1 for fully cracked material points. And as a consequence, by increasing its value, it reduces the stiffness of the solid, as you can see in the first integral. Secondly, there is a gradient term and consequently a length scale. The model is non-local, which ensures mesh independence. Results are mesh independent as long as the length scale is resolved. So at the end of the day, we have a model that is physically sound, based on Griffith and in the thermodynamics of fracture, and at the same time, computational very compelling. You can get a good overview by looking at the balance equations. The first equation is the solution to the deformation problem, the standard balance of linear momentum with the phase field degrading the stiffness of the solid. And the second equation is the phase field evolution, sort of a competition between the strain energy density of the solid that increases with mechanical straining and the toughness, a material property. So just by solving this simple system, we can predict in both 2D and 3D very complex cracking patterns, such as branching, merging, initiation from arbitrary sites, complex trajectories, and all these without convergence issues or the need for remeshing. You can see some examples in the slide. And what we have done is to propose the first formulation of phase field fracture for shape memory alloys. And there are two key elements in our formulation. One is that the toughness of the material can be made dependent on the martensitic volume fraction. We know from experiments that the toughness of the martensite and the austenite phases can be quite different. So we believe that it is important to have this heterogeneous fracture energy. And we do so by using simple homogenization. The second element is the fact that the driving force for fracture is not just the elastic strain energy, but also we consider the contributions from the transformation strengths. And we implement these numerically into finite elements. I'm going to show some representative examples of 3 boundary value problems where we model crack propagation with this formulation. The first one is a boundary layer model that is widely used in fracture mechanics. Then we model a square plate with a crack, a paradigmatic benchmark in phase field fracture, and finally, I will show an asymmetric double notch bar. For these numerical experiments, we have coupled our new phase field fracture formulation with the unified model from Lagodas and co-workers to capture the constitutive response of shape memory alloys. In the left table, you can see the shape memory alloy material parameters that we use. We model an atomic nitinol, following the experimental data provided by Strand and all. A uniform temperature of 320 Kelvin is adopted following the experiments, but its influence is investigated and the model can be used with varying temperature. In the right figure, the comparison between the calibrated model predictions and the experimental data from the uniaxial tension tests is shown, and we observe that the smooth hardening capabilities of the model enable attaining a very good agreement with the experiments. So the first boundary value problem is what we typically call a boundary layer formulation. And our goal is to compute crack growth resistance curves, or so-called R curves. The concept of a boundary layer formulation is illustrated here. For a cracked solid, the crack tip stress state is characterized by the stress intensity factor Ki, assuming mode 1 conditions. So we prescribe a specific stress intensity factor by modeling a circular region and prescribing in the outer boundary the displacements according to the Williams elastic solution. Remember that the high stresses near the crack tip will trigger a phase transformation, but as long as this transformation zone is small, this approach can be used. So we use this boundary layer formulation to apply a remote load as characterized by the remote stress intensity factor Ki, and to compute the crack extension delta A using our phase field formulation. This gives us crack growth resistance curves. The results shown here analyze the influence of, in A, the phase field length scale, in B, the toughness definition, in C, the crack density function, and in D, the temperature. In all cases, the model predicts a toughening effect, raising of R curve, that is associated with the energy dissipation due to phase transformation, as observed in the experiments. In A, we see that when we lower the phase field length scale, which is equivalent to raising the material strength, we get a higher R curve. In B, we see significant difference between assuming a homogeneous toughness or making the fracture energy dependent on martensite volume fraction by using the rule of mixtures. The martensite phase has a smaller toughness, so cracking initiates before. In C, we show that the so-called phase field 81 model leads to less dissipation relative to the standard phase field 82 model. And finally, in D, we evaluate what happens at a temperature below the austenitic start temperature, such that no reverse transformation takes place upon unloading. We see more dissipation at smaller temperatures as the transformation stresses are smaller. Here, failure of a cracked square plate subjected to tension is analyzed. The results obtained are shown at the right in terms of the force versus displacement response, with the contours of martensite volume fraction and the phase field fracture parameter, phi, at different stages embedded in the figure. Difference from the response commonly observed in this classic benchmark are notable. We all know that in a linear elastic homogeneous material, the plate fails in an unstable manner, with the force versus displacement curve showing a very large drop immediately after reaching the peak load. However, in this case of shape memory alloys, a significant toughening effect is observed. and there is an initial drop in the load associated with the first instance of crack growth, but then the crack progresses in a stable manner until complete failure of the sample. The toughening effect observed is related to the energy dissipated due to transformation. An asymmetrically notched plane strain bar is investigated here to model mixed mode fracture and crack coalescence. The results are shown in the right. Contrarily to the response observed in the previous slide of the square plate, a sharp drop in the forces versus displacement curve is observed, which is indicative of brittle fracture with little inelastic dissipation. The inelastic region is confined to a small area in the close vicinity of the tips of the notches. No inelastic or shear bands are observed, such that as soon as cracking initiates at the notch tips, the cracks coalescence and the unstable cracking is observed. So let me now show you some fatigue results. Phase field fracture models have also been extended to model fatigue crack growth. The idea is to define a fatigue degradation function that reduces the toughness of the material with increasing number of cycles. And the beauty of it is that well-known fatigue behavior, such as Perry's law or SN curves, can be predicted by our model. So they are an output of the model, not an input, as it is typically the case. So now I'm going to demonstrate the capabilities of our modeling framework in capturing fatigue crack growth by simulating cyclic damage in a stent, which is a paradigmatic application of shaped memory materials. This case study also serves to showcase the computational efficiency of the framework and its applicability to the modeling of computationally demanding large-scale 3D boundary value problems. So stents are small cylindrical tubes that are placed into blood vessels, arteries, or other ducts to hold the structure open. Nitinol is a popular material choice in stent manufacturing due to its biocompatibility and capacity to expand by recovering its elastic deformation after the constraining delivering system has been removed. However, fatigue resistance is often the limiting design criterion, since the stent is subjected to repeated contraction and expansion during the systolic and diastolic cycles. Current fatigue design models for stents commonly use Goodman's and other empirical methods to estimate the number of cycles to failure by extrapolating from the stress-strain state of the first cycle. We aim here at providing a more mechanistic approach using a phase field fatigue framework that can predict features such as SN curves or the Paris law as a natural outcome of the model. The finite element results obtained are shown here. The figure at the top shows the deformed shape of the model during the 4 stages of the analysis, the crimp and expansion stages of the deployment phase, and the systolic, compression, and diastolic expansion stages associated with each pressure cycle. A significant amount of damage occurs during deployment, but no cracking is observed. This is also the case for the phase transformation. Most of it takes place during the deployment phase. In the bottom figure, the contours of martensitic volume fraction at the end of the crimp expansion deployment process are shown. The martensite volume fraction contours show that the martensite phase is localized in the edges of the stent struts. This is also the location where cracking initiates. While the phase field reaches high values during the deployment stage, 29 cycles of compression expansion pressure are needed for cracks to initiate. These surface cracks initiate in the regions where phase transformation took place during stent deployment. The crack region, phi = 1, extends with increasing number of pressure cycles. And after 50 cycles, it has extended over a significant part of the stent, including the bridging areas between struts. So in summary, the example demonstrates that the framework presented here can be used to estimate the lifetime of medical stents for arbitrary geometries, boundary conditions, and material properties. So I will conclude by saying that we have presented the first phase field fracture formulation for shape memory alloys. The model can capture both fracture and fatigue damage and includes the main features inherent to the constitutive behavior of shape memory alloys. We have demonstrated the potential and the robustness of the computational framework by addressing several paradigmatic 2D and 3D boundary value problems involving subcritical crack growth, unstable cracking, crack coalescence, and fatigue crack growth of a nitinol stent. Thank you very much for your attention, and many thanks to the European Space Agency for supporting my research. In our paper, you can find more details about this work. Thanks.